All right, this is the third and final video for the Atwoods machine, and we're kind of leading up to difficulty here. So you can kind of already see from the diagram and the picture that this is probably going to be the most difficult out of all three. But it's definitely not doable, or not undoable, I should say. Sorry about that. It is definitely a doable problem because we're still going to use the exact same skill set we've been using all along, and that is treat the system as one thing for acceleration and treat the system separately, or in other words, choose a box when you want to solve for force tension. Now, what makes this one highly enjoyable, I use that term kind of loosely, but it's because we're dealing with a ramp. And if you recall from Unit 4, the ramp was probably one of the more difficult problems because you had to draw the force diagram correctly. So let's go ahead and do that. Let's draw the easy one first, and that's the 8 kilograms. So you think about what forces are acting on the 8 kilograms, and what does that look like? Okay, you have force gravity going down, and I'm going to do that FG8. So we know that that's the force gravity of the 8 kilogram. And then you have force tension up, and that's it. That's all there is. Real simple there. The 5 kilogram one, on the other hand, that one is a little bit more difficult. So we've got force gravity going down, and I'm going to label that FG5. We've got force normal that's going perpendicular to the surface. We've got its force tension that's going parallel to the surface. And then this first problem, let's go ahead and say that there is, actually, let's say there is friction. I'm going to say there is a coefficient of kinetic friction between the 5 kilogram block and the surface of 0.15. Okay, because we're going to deal with friction anyway, we might as well deal with it right now. So there is friction. All right, now, I'm not going to draw in friction yet. And the reason why I'm not going to draw it in yet is because technically, you don't know which direction it goes. I mean, you can probably think, using a little bit of common sense that, okay, since the 8 kilograms hanging over the edge and the 5 kilogram has less mass, and that means it's going to accelerate upwards, up the ramp, and therefore friction would have to be facing down. But, like I said, you don't technically know that yet. You can't assume that until you know numbers. And like I said, this example, it's really straightforward. It's you can kind of guess that that's what's going to happen, but some situations are not going to be as straightforward, so you need to know. And so I'm going to teach you how you can solve and know which way the friction goes based on numbers. So let's just work with what we've got so far. So when I look at my 5 kilogram block, the force diagram is 3 forces, normal, tension, and gravity, 5, and the gravity, if you remember correctly, the gravity is diagonal when we're dealing with ramps. So we need to split the gravity up into its x and y component. And remember, I told you in the previous videos, draw the y component of gravity first. So the y component is going to go down like this. So that's FGY. And then the x component is going to go down like that. Notice how I draw the x parallel to the ramp. And so that's FGX. And the reason why I tell you to draw the y component first is because when you draw the y component first and you get this angle right here, that angle will be equal to the angle of the ramp. So if the angle of the ramp is 30 degrees, that angle right there is 30 degrees. Okay, with your right angle being right there. Okay, so now what we've got is we've got our force diagrams drawn. Now let's see if we can figure out what the numbers are as we go through. So we know that the force gravity of the 5 right here is 50 newtons. Okay, but we split that up into its x and y. And so we need to figure out what FG x is, and we need to figure out what FG y is. When we're solving for FGX, which is this one right here, okay, we're going to do that by taking sine of 30 degrees times the hypotenuse, which is 50. And that's going to give you 25 newtons. So my force gravity in the x direction, I'm going to go ahead and erase that here. And I'm going to put that in there. That's 25 newtons. For force gravity y, I'm going to do cosine of 30 times my hypotenuse. And cosine of 30 is 0.866 times 50. That's going to give me 43.3 newtons. So that's my force gravity y. Okay, so I figured those out. What else can I figure out? Well, I know that the force gravity from the 8 kilogram block, I know that that one's 80 newtons. Okay, and then since the normal is equal to the force gravity y, I know my normal is 43.3 newtons as well. So that basically only leaves the tension forces that are unknown, which that makes sense because we know we have to solve for those. Now, here's how you know which direction the friction goes. Okay, think about what cancels out. Okay, well the force tensions cancel out. The force normal cancels out with the force gravity y. And then so what vectors, what force vectors do you have remaining? You've got the 25 newtons. That's going in the x direction. And think about what does the 25 newtons want to do? It wants to pull the 5 kilogram block down, therefore raising the 8 kilogram block. The only other force that you have is the 80 newtons that's right here. And what does that want to do? Well, it wants to pull the 8 kilogram block down and the 5 kilogram block up. So we can see that the 80 newtons that's coming from force gravity here is in contention with the force gravity x that's right here. They're opposing each other. And so when I go to write my force net, okay, I already know that that's going to that they're going to be opposing each other. But here's how you know which direction friction goes, because we can't forget friction. I know we've left friction out. Don't forget that it is there. We need to figure out which direction it goes. Right now, which one's winning? The gravity x of 25 newtons or the gravity 8 of the 80 newtons? Obviously the 80 newtons. So right now, what does the system want to do? It wants to pull the 8 kilograms down, therefore pulling the 5 kilogram up the ramp. And if the 5 kilogram box is moving up the ramp, friction has to oppose motion. So that's how we know. That's how we have proof that the friction points down the ramp. It's because it wants to oppose the motion of the 5 kilogram block moving up the ramp. Now that we know that, we need to figure out what the force of friction is. So let me move this up here, get that out of my way. All right, my force friction is going to be my mu times my force normal. Well, my mu is 0.15, and the normal force acting on the 5 kilogram block is the 43.3 newtons. Notice it's not 50, it's 43.3 because the normal is equal to the gravity y. So my force friction is just going to be approximately 6.5 newtons of frictional force. So I'm going to write that up here in my force diagram. All right, so let's figure out what we've discovered so far. We've already figured out that the 80 newtons and the 25 newtons, those two vectors are opposing each other. But we now have that third vector, that frictional force in there, that's not balanced out either. And so my net force needs to take that into consideration as well. Now, which two vectors are helping each other? Well, the 25 and the 6.5 both are facing down the ramp. So those two together help each other out. And they help oppose the 80 newtons that's over here. So really my force net is 80 newtons minus the frictional force minus the gravity x, and that's equal to the mass times the acceleration. So my net force is 80 minus 6.5 minus 25. My net force is 48.5 newtons, and that's equal to the mass of the entire system, which is 13 kilograms, times a. Divide by 13, and my acceleration is 3.73 meters per second squared. Now, I didn't actually ask which block am I solving for, but let's assume it was asking to solve for the acceleration for the 8 kilogram block. If that was true, then that means it's going to be a negative 3.73 meters per second squared, and that's because down is negative. Okay, because once you analyze the 5 kilogram block, the 5 kilogram block is on a ramp, and so you have to imagine that you have a new axis just like that. So if I wanted to know what's the acceleration for the 5 kilogram block, it would be a positive 3.73 meters per second squared, since up the ramp would be positive. Okay, now let's do the second part of the problem, and that is what's the force tension. I'm going to go ahead and erase this stuff right here since we don't need it anymore. Force tension, you can choose whichever block you want. I'm going to go ahead and choose the 8 kilogram block because it has less forces acting on it. So the 8 kilogram block has two forces that are acting on it to contribute to its force net. It has the force tension and the force of its gravity. So if I plug in those numbers, force tension is what I'm solving for. plus force gravity. The force gravity is 80, but it's pointing down, so it's a negative 80. That's equal to the mass, which is 8 kilograms, times its negative acceleration of 3.73 meters per second squared. Clean that up a little bit. We got force tension minus 80 equals 8 times negative 3.73, which gives me negative 29.85 newtons. Add 80 to both sides, and I end up getting a force tension of 50.15 newtons. All right, let's go ahead and look at one more. Since these ones can be a little bit more difficult, I will go ahead and work this one out as well. Let me go ahead and move. It's not going to let me, but remember over here, we're going to assume on the block that's going up and down, we're going to assume that it's going only in the vertical direction. Sorry, I was having a little technical difficulties there. So what I was saying over here is that since the 9 kilogram block is moving up and down, we just need to establish a positive direction in the vertical. It doesn't matter about the horizontal since there is no horizontal movement for the 9. And then for the 4 kilogram block, since it's on an axis, I'm going to tilt my axis here, and I'm going to say, and actually I really don't even need to do with the vertical. I'm just going to say up the ramp is positive. Okay, so that'll be our coordinates there. And let's say I wanted to know what is the acceleration. I'm going to write that up here. What's the acceleration for the 9 kilogram block? What's the force tension? And we're going to say that you have a coefficient of kinetic friction of 0.2. Okay, so let's go ahead and do that. Remember, we got to start out with force diagrams. So we've got the 4 kilogram block has force gravity down of 40 newtons. That breaks up into the y component and into the x component. If this is 20 degrees, that means this is 20 degrees. We've got force normal, that is facing up. We've got force tension, that is facing along parallel to the ramp. For over here, we got the 9 kilogram, has a force of gravity of 90. Its force tension is facing up. And then now let's go ahead and solve for what is the y component and x component of gravity. If I want to solve for the x component, my x component is sine of 20 degrees times 40, which is my hypotenuse. And that is going to give me 13.68 newtons. So that's for the x component. And then for the y component is cosine of 20 times 40, which is my hypotenuse. And that gives me 37.59. So 37.59 newtons is my y component, which is also my force normal. Okay, so I'm going to go ahead and erase that since I don't need that anymore, so I can save my space here. And then I look at what vectors cancel each other out. I have not forgotten about friction, but remember I got to mathematically figure out which one is going to which one's going to win, so which direction force friction will go. Normal will cancel out with gravity y. Tension will cancel out with tension. And so I've got my gravity x wanting to pull down the ramp of 13.68 newtons. And I've got the gravity over here wants to pull the other direction. And so it's pretty clear from those two values that the block wants to accelerate down this way, meaning the 4 kilogram block wants to move up the ramp. And so a 4 kilogram block is moving up the ramp, friction has to point down the ramp. And let's figure out what that friction is. Friction is just equal to the mu times the force normal. The mu is 0.2, and the normal force is the 37.59. And so 37.59 times 0.2 gives me a force friction of approximately 7.5 newtons. Okay, so now I'm going to go ahead and get rid of my calculation there for force friction because we have that. So now that I've got my entire force diagram with all my values in there, let's go ahead and figure out what the acceleration is. Force net equals mass times acceleration. What is the force net acting on this system? Well, it's the 90 newtons, but then friction takes away from it, and so does gravity x. And so 90 minus 7.5 minus 13.6 gives me a net force of 68.9 newtons. And it's that's equal to the total mass, which is 13 kilograms, times A. And my acceleration is going to be 68.9 divided by 13. That's going to be 5.3 meters per second squared. And is it negative or positive? Well, since I'm asking for the acceleration for the 9 kilogram block, the 9 kilogram block accelerates down, and down is negative, so that's a negative 5.3 meters per second squared. Now, for number 2, I'm going to go ahead and solve for the force tension, and I'm going to use the 9 kilogram block to do that. So the 9 kilogram block has the force gravity down of 90 newtons, and it's got force tension going up. So my force net acting on the 9 kilogram block is a combination of the tension plus the gravity. My tension is what I'm solving for. Plus, my force gravity is the 90, but it's got to be negative 90, because 90 is pointing down. That's equal to the mass, which is 9 kilograms, times the acceleration of negative 5.3 meters per second squared. If I clean that up a little bit, force tension minus 90 equals 9 times negative 5.3. That's going to be negative 47.7. Add 90 to both sides. And my force tension, which I'm going to write it up here because I ran out of space, my force tension is 42.3 newtons. This concludes the video on Atwoods Machines Part 3 and also concludes the Atwoods series.